By the end of the day, we hope that you'll have a better understanding of transportation as a field and transportation engineering. We hope you'll understand more about what kind of research we're doing here related to transportation, that you'll have a glimpse into some of the local transportation issues that we are working on here locally in Gainesville, some transportation-related careers that you can take back and talk to your students about, some STEM activities that could be incorporated into your classroom, and also additional resources both online and in the community that you could use potentially in your classroom. So any questions at this point? Logistics, if you want anything to eat or drink while we're having our meeting, please go ahead and help yourself. If you do need to go to the bathroom, you just have to go back out to the main hall to the right, and it's about halfway down the hall on the right. So with that, we're going to go ahead and get started, and Sybil, we'll go ahead and pull yours up. So speakers, you can present sitting or standing, whatever is most comfortable for you. And okay, great. And I think, do we have a clicker? Did you know, Patrick, did that clicker, oh, you got it to work? Great, thank you. Super. Here.
All right. So good morning, everyone. And again, thank you very much for being here and your interest in transportation engineering. We hope that we'll be able to provide you a very good overview of a lot of things that are going on at UF and in Gainesville today. And as Ondine was mentioning, we also appreciate a lot of feedback from you in terms of how we can engage with you, with our students, the K-12 students, as we move along in this process. Okay. So I guess teachers like to ask questions, right? So open it up. Like, what do you think a transportation engineer is trying to achieve? What's our big goal?
Transportation.
Efficiency. Okay. Efficiency. Safety. Okay. What else?
Solve traffic issues.
Solve traffic issues. Okay. Okay. So, and the teacher also has some answers as a backup, right? Right. So yes, all of that, and we'd like to think of transportation engineers as, you know, people who try to provide mobility options, right? We should be able to travel wherever we want to go, whenever we want to go, and goods and services should be able to get to us, get to the shops, etc. So we are talking about transportation of people and freight. We talk about efficiency. We don't want to get stuck in congestion, so we want to alleviate congestion. We want people to be able to move as quickly and efficiently as possible. We are in the business of improving reliability. If it takes you 5 minutes one day and 25 minutes the other day, it's very frustrating for the same trip, so we want to do that. Safety, that's a big goal. We measure it in terms of crashes. We have new ways of measuring it. We'll talk about that later. And we want to increase convenience and do it all these things with limited budget, limited resources, and ensuring that we are not adversely impacting the environment in all our processes. So in the overall, we kind of think ourselves as like, you know, people who try to improve quality of life of our people. If people are able to move about, accomplish whatever they want to do, have goods and services delivered to them, that's a big part of having a very good quality of life. So that's a big vision, that's the big goal of what we are trying to achieve. So the way we go about doing this, we started the planning process. All major cities have a long-range transportation planning. We're always thinking out 10 years, 20 years, 25 years into the future, trying to anticipate how many people will be living here, what kind of people will be living, will they be young or old, where would they be living, what would the land use patterns be, what are other technological changes that are happening, so what would be the demand for transportation into the future. So that's a standard part of the transportation engineering process. So once we have some plans, and then we can start thinking about, like, you know, what kind of a transportation system do we need in place so that we can take care of this future demand while making sure that, like, there's no congestion, there is reliability, there is safety, we are not messing up with the environment, so on and so forth. So it's an integral part of the process, right? And then once we plan, then we have to design the specific systems. So this could be designing a specific piece of roadway. What is the geometry? What is the elevation, etc. If you're talking about transit systems, it could be what is the frequency, what is the route. So there's a design part of it, trying to get into the nitty-gritty details of what we want to actually build or implement or deploy in the field. And the next process is actually constructing it or building it or deploying it, right? So if it's a road, we have to again go through the process of actually constructing it. If it is a certain technology or a signal system, then we have to deploy it and make it work. And then we have to actually operate the system. So there are traffic engineers who are operating all the traffic signals right now. And there's an agency that is operating all the buses. So there's a lot of operations, daily operations that goes on behind the transportation engineer. And we are talking about a lot of mechanical things. Things break down. They have to be upkept. So there is a whole aspect of maintenance to it. So something goes wrong, what can we do? How can we maintain? How can we ensure that there is no deterioration of service at any point in time? But we cannot keep indefinitely maintaining a system. Things do go wrong at some point. It has to be replaced. So while we maintain, we are also planning for the future. So at any point in time, all these steps are happening. We are thinking about Gainesville 20-25 years from now. Some of the plans have already started going into the design phase. There is construction going on, deployment going on. We are maintaining and operating, etc. So all these things are happening simultaneously in order to take care of these transportation systems. Okay. And this process, this approach is not new. We've been doing this for years and years and years. So the next question is like, what is really new? What is something that's new and exciting and fun and challenging that's happening in transportation engineering, which can have a potential huge impact on how we do business, okay? And so what's new? Well, first we're talking about things being autonomous, self-driving cars. We keep hearing about all that stuff, right? So we are slowly taking the driver away, and then there is technology that can drive the vehicles around. So there is a lot of autonomy, or the vehicle can make the own decisions. We're talking about connected systems. Things can talk to each other. A vehicle can talk to another vehicle. That's what we call as V2V connectivity, a vehicle-to-vehicle connectivity. So if a vehicle is upstream, it is detecting some unsafe conditions, it can really talk upstream to the other vehicles and say, hey, there's something wrong going on here, so just be aware of it, right? And then we're talking about V2I connectivity, vehicle to infrastructure. So cars can talk to signals and other infrastructure elements along the way. So we're just talking about connectivity between vehicles and infrastructure. And in fact, it's going to what is called as V2X connectivity, which is vehicle to everything, right? Vehicles can talk to pedestrians, vehicles can talk to infrastructure, and so on. I mean, just to give you an example, if you want to try out, there's a little app called Enlighten, E-N-L-I-G-H-T-E-N. If you want to try it, there's one of the things. So that's an app which can actually talk to the signals, and it works in Gainesville. And so if you have this app on and you're driving and you're approaching a signal, the app can actually tell you if the light is red, it can tell you how much time before it turns green. Or if you're approaching and it's already green, it can tell you what speed should you maintain so that you can get through the signal if it's feasible. Okay. So just try it out. It's already working. Yeah, I mean, don't blindly believe it. The app doesn't know about vehicles in front of you or the driver characteristics of those people, but it's talking to the signal. The signal is telling this is the current state right now, and this is when it's going to change. So it's communicating that information, and the app is converting that information into usable information for the drivers. So again, this is something that works.
It's called Enlighten.
Enlighten, E-N-L-I-G-H-T-E-N.
Okay.
Yeah. And I guess you'll probably be driving today, so maybe you can give me or like, you know, if you're meeting Emmanuel, then he can also tell you more about that and other apps. Yeah. So anyway, the point is things, the communication does not have to go through the humans, but the things are starting to talk with each other already. Right? And we are moving to a shared economy. and not just in transportation, like, Airbnbs are kind of becoming a big competitors to hotels. So just like that, we have Uber and Lyft and things like that. So we are going from a model where you either had a private mode of transportation that you operated, or the government was providing the buses. So those were the extremes. But now you have, we can become providers of transportation system. We can become an Uber driver or a Lyft driver. We can provide services, but at the same time, we are also sharing the vehicles and services from other people. So the role of the private sector is becoming very, very important and very dominant. And again, this is not just in the case of vehicles. We are talking about scooters and bicycles and all that stuff as well. And things are getting more and more personalized. So what I mean by that, 10, 15 years ago, if you want to find a route from point A to point B, you'll probably open a map, a paper map, which probably doesn't even exist now, right? And the map just gives us all the possible roads that exist in the area. It is not telling me how do I get from point A to point B. But today, people are saying, don't give me all the information that I don't want. Just tell me how I can go from point A to point B. So there is a lot of demand for personalized transportation, personalized information, which as transportation engineers, we have to provide. Okay? And related to this, personalized is on demand. Okay? People want the information when they ask for it. So which means that we should be ready to be able to provide customized information to people, and we should have the capability to calculate all these things when they ask for it rather quickly. So essentially, intelligence is being added to a lot of these systems. So all our systems are having sensors, so they are able to detect what is going on, and they also have some kind of a knowledge, this is kind of slowly increasing, where they can figure out when something is going wrong, something is happening that is different, and then they can communicate to a central server or to an agency or to a traffic engineer, and then they can reflect back some changes to the transportation system in practically real-time information. So we are really talking about all these kinds of disruptors that are happening to the transportation engineering, and where transportation research at UF is really coming in is at the intersection of these two. So we have this process of doing transportation engineering that we've been using for a really, really long time, and then we are seeing all these phenomenal changes that are happening. So how do we reconcile the two? How do we plan for a transportation system for Gainesville considering autonomous transportation? Like many of us have not even experienced what it is to be in an autonomous car. We don't know how it will behave when it's torrential rainfall one afternoon, right? So how do we even plan for it? Connected signals. So how are these technologies going to talk to the infrastructure? How do I upgrade my signals? We're talking about shared, right? Like how do I operate my system under shared mobility situations? And one of the issues that is becoming of importance is what is called as curbside management. With a lot of Uber and Lyft trips happening, pick up, drop offs. I mean, where are they going to pick up and where are they going to drop off people? What does that do to the transportation system if you have Uber cars dropping off people, things like that? Like personalized, how do I provide customizable information to people? So essentially the intent of the Transportation Institute is to bring together researchers from a variety of expertise to be able to look at how we can still do transportation engineering in the context of all these changes that are happening. And what that means is that we are not just looking at civil engineers. So traditionally, transportation engineering has been a stream within civil engineering. And civil engineers have been the ones who've been dealing with transportation all the time. But now we are kind of expanding that to say, hey, we need to talk to mechanical engineers. They are the ones who are designing all the self-driving cars. We need to talk to all the electrical engineers and electronics engineers. They are the ones who are doing the sensors. We need to talk to the human factors people. We need to figure out how human beings and machines can communicate. When you're traveling on a freeway at 70 miles per hour, and if you have to communicate with your car to make a very quick decision, that communication better be very efficient, right? So we need to talk to computer scientists, right? How can we do millions and millions of data processing and get the information to the right people very quickly. So there's a lot of analytics going on. There is a lot of programming that's going on. We need to talk to occupational therapists, right? So we have to be very inclusive in the technology. How can we help the older drivers? How can we help the disabled people to take advantage of these technologies? So we need to talk to occupational therapy folks. So essentially, UFTI is kind of an umbrella organization, an institute within UF that's trying to bring in people with a large variety of expertise to be able to address all these kinds of issues at this point. Okay? And you're going to be hearing a lot of acronyms today. I mean, Ondine mentioned STRIDE, which is a funded center from the Federal Highway. I've been talking about UFTI, which is kind of an umbrella organization of faculty interested in transportation, but that's within UF. And iStreet, by the way, this has nothing to do with Apple, you know, funded by Apple, but still, it's an acronym. So this is an initiative under UFTI and STRIDE, and it's one way of trying to address all these questions. And it is a collaborative effort with three major partners: the university, the City of Gainesville, and the State Department of Transportation. So essentially, the State Department of Transportation is providing a lot of funding for the research. The UF faculty are doing the research. The city is providing access to infrastructure to actually be able to put sensors on the road. And then we are also collaborating with a lot of private sector vendors so that we can start putting some technologies in and actually start evaluating, you know, does it really help improve safety? Does it really help improve mobility? How do people interact with it? I mean, how does it work? So on and so forth. So some of the projects that you're going to be hearing about in a little bit more detail are related to iStreet, but I guess a lot of the research that's happening is either a STRIDE funded project or it's a UFTI iStreet project or other projects that are going on. It really doesn't matter where the funding is coming from, but I guess the idea is to communicate the breadth of research and the new scope of what's going on. So I guess, you know, what the main points that we wanted to make are that it's really, we're talking about very, very transformative changes. If we were having a discussion about transportation engineering 10 years ago, many of these folks would probably not be in this room. They would probably not be interested. The mechanical engineers, the computer scientists, the human factors people, the occupational therapists, there's probably no reason for them to be in a transportation engineering setting, but they're all here. We're all talking about this. Computer scientists, yes, not forgotten. I think so. It's really because of the transformative changes, and then so we really need a lot of new thinkers and new ways of thinking of addressing the problems. And what we're really hoping with the STRIDE Center is that we can start engaging K through 12 students in this process as well. We don't have to wait until students come to college to get them to start thinking about transportation problems. You know, whether you're interested in mathematics or whether you're interested in analytics or programming, whether you're more interested in technology, whether you're more interested in economics, even if you're interested in communication and art, I think it really doesn't matter, but there's a role for all of these things in the transportation education. So I think that's really the broad objective. You know, we want to engage all of you, and through all of you, our K through 12 students. And as Ondine mentioned, this is kind of an initial step, and we are hoping that this will be a two-way communication as well. We are looking forward to learning from you as to what we can do to facilitate that and how we can move forward. So that's broadly what I had in terms of introduction. I don't know if there's...
We're going to we could take one question for each person, but I want to make sure we stay on task because we want to get everybody covered and make our shuttle bus.
Okay.
So if we have one question from anybody, you're welcome to raise it. Looks like you covered it all. That was great. Thank you so much.
All right. Thank you.
And Siva did a great job of also clarifying that while I'm part of STRIDE, a grant-funded project, it's under this larger umbrella of the Transportation Institute, which is some of the stuff that you have in front of you.
I do have a question.
Yeah.
So how is, you mentioned, well, this is for education, but combining education with all of this, is it just things like this that happen?
So no, we do some K-12 outreach in the local schools, which we'll talk a little bit about this afternoon, and we want to build and expand on that. So one of the conversations that we can kind of start today is like, what would you like to see that we could bring to your school, or we could provide better training for teachers in some of these things? So, yeah. Okay, great. And
I'd like to introduce myself. My name is Wayne. I am a new assistant professor in industrial systems engineering. I started last year, so I'm relatively new to Gainesville. It was great to sort of meet the local community that is, expanding the future, hopefully gators for my future students in the future. I'm currently looking for students still, so might be too early for your students, but hopefully down the line. So what I'm going to talk about today is slightly different in terms of style. I'm mostly going to talk about the human factors work that I do as an industrial and systems engineer, and a little bit about our capabilities and the research topics that I personally look at. So human factors is, there's a definition up there that states that it's the engineering discipline that deals with all aspects of human characteristics in the design of things people use in their everyday work and daily lives. The goal is to improve the interaction between people, technology, and the environment to optimize human well-being and overall performance. So this is what I work on. And the broader sort of field of industrial and systems engineering really focuses on how we can optimize things across different domains. So in human factors, we work on optimizing human performance with the systems they interact with. And we try to make that more efficient, we try to make it safer, we try to make it more enjoyable for people to use. So the Human Systems Engineering Lab is the lab that I'm a co-director of. We started within the last year when 3 of us were hired to build this lab within Industrial Systems Engineering. And we have a number of different facilities and capabilities. And I just wanted to talk through some of these because they showcase the different ways that we can measure and understand human behavior and performance. So up here at the top, we have our US Advanced Driving Simulator facility. One thing I want to note is all of this is still under construction. If you ever hear construction going on outside that's not associated with the big building, it's probably for our lab because right now it's just like a gray empty room and our equipment is just waiting for it to be put in. But one of the things we will have coming soon is the 6 Degree of Freedom driving simulator. So in this driving simulator, we can study human behavior, human driver behavior under different conditions in a way that is safer than if we had people on the road. So we can throw distractions at them, we can throw like bikes interrupting their path, and then we can see what driver behavior is like under those conditions. We also have a human-robot interaction facility where we can understand how humans interact and understand how other robots work within their work environment. So this will be very important as automation becomes much more prevalent in our daily lives. So, like how do you understand what this robot is doing and what the robot's intent is? In this example, the eyes are something that might provide a visual cue that designers of these systems can use to try to communicate that intent. We also have a motion analysis and activity recognition facility. So a lot of human factors work deals with ergonomics. So, gait analysis, human pattern analysis, biomechanics, and we have a number of systems in the top left here that include cameras, force plates, and all of these help us understand how humans walk, how they interact with different devices and the forces that they have to deal with. We can study sort of more psychological and attentional aspects by using eye trackers and physiological sensors. So in this example, we can see where the human driver is looking as they interact with a smart device. We have facilities for understanding or observing humans interacting with technology. So this safety critical systems user experience facility. And we also do a lot of work in human factors when we go out in the field. So we actually go into the domains that our workers or our operators are dealing with, and we try to understand all of the complexities of our work environment. So that was about our capabilities as an entire sort of department, as a discipline. I'll talk a little bit more about my own work. So my work deals mostly with how people, individuals, deal with new and emerging technologies and how to design those technologies to better facilitate their goals. So some examples of this are on the left-hand side. I study how new smart devices like smartwatches might lead to distracted driving behavior. And I've also studied how tools like decision aids can improve medical dispatch. So a lot of my work deals both in transportation and in healthcare domain. And to do this work, I use a variety of different methods. Human factors is an interesting blend between psychology and engineering. So we spend a lot of time understanding how humans think and how humans work, and then we apply it to designing interventions and technology. So we use field observations, we use questionnaires, we use interviews, but we also do a lot of experiments where we might introduce a new technology in the field, see how that changes behavior, we compare it to a baseline where they're using the old technology. The other thing that I want to talk about is because I'm in an industrial and systems engineering lab, department, one of the things we sort of focus on is a systems-based approach. Humans are only one part of a much larger socio-technical system. There is the humans that we want to support. There's the technologies that we're putting into the system to support the work. And each of these humans, they have goals and tasks they want to accomplish. And it's really the interplay between the three that we need to understand in order to facilitate that better behavior. And all of this is also put into a larger sort of broader work environment, which has constraints. So that could be the organization that they need to do the work in. It could be the political landscape that they have to work under in terms of laws, or cultures that they have to deal with in terms of understanding people's background. So the transportation problem that I'm going to talk about more today is about notifications during driving. So we know that distracted driving is a problem. I think nowadays we have a lot of sort of knowledge about how texting while driving can be very bad. In fact, it's actually worse than drunk driving in terms of risks to the driver. But we're also getting a lot of sort of new technologies like smartwatches that are not as well understood. Smartwatches have been marketed as a way of reducing distraction, right? You don't need to pull out your phone anymore when your Apple Watch buzzes at you. So that's supposed to minimize distraction. However, even those sort of small movements of attention away from the forward driving scene can lead to detrimental behavior. And that's something that hadn't been studied before. So we conducted some studies that studied how wearable technologies might act as distractors. We did this within a driving simulator environment. So I evaluated how notifications on smartphones might be different from getting notifications on a smartwatch. So this study was done quite a while ago. That's a very early smartwatch. That was back in like 2012, 2013. Smartwatches have gone a little bit fancier, but the underlying usage of smartwatches is still relatively the same. You get a vibration on your wrist, you look at it, and then you're supposed to go back to what you're doing. So what we did was we sent some notifications on both these devices, and we observed how often they looked at the devices, how much time they spent looking away from the forward driving scene, and what their brake response times would be if we had a lead vehicle brake right in front of them. Because that's a good way of sort of measuring driver performance. And what we found was, that's actually a typo. So participants actually did not think that smartwatches were more dangerous than smartphones. So we asked them in these sort of post-experiment questionnaires, what was the perceived risk between these two devices? And they were like, no, smartwatches aren't any more dangerous. But in our actual experiments, we saw that smartwatches resulted in some detrimental behaviors. They spent longer looking away from the driving environment with smartwatches than the smartphone, and there were slower brake response times when compared to smartphones. Some of this might be just because people are less familiar with using smartwatches. People have developed some very strong and well-practiced habits in responding to notifications with smartphones, and maybe they just haven't developed the same ones for smartwatches. But this sort of disconnect between their perception and their actual behavior is something that is worrying, and that's something that requires further study. One of our sort of more current projects is we're also trying to study distracted walking behavior, because this is something that is also quite worrying, especially on a college campus. One of our sort of first steps in this was we were looking at how many people on US campus, how many of our students and staff and faculty are walking while distracted on their smart devices. And we saw approximately 1 in 5 pedestrians were actually using a smartphone or smartwatch while walking across campus. And this can be worrisome because when people are interacting with these devices, not only does it take your attention away from the world, it can also change your gait behavior. So you might be at higher risk of falling if you're distracted. You might not be able to respond to environmental disturbances as much, so you might not notice that rock. And because your gait is different, you might have a higher risk of falling. And these differences in gait performance might actually be more influential when you have older users of these devices. So it's not just young students who are distracted these days. Technology is so prevalent that everyone uses it to help their daily lives. So you have an older individual who might be distracted and might have impaired gait, that can lead to higher chances of fall. And this is something that we're studying in an upcoming study this summer. Okay, so I just wanted to finish off by talking a little bit about the roles that human factors engineers might have. When I was in high school, when I was in elementary school, I didn't know about the field of human factors. I was really interested in psychology. I was really interested in engineering. And I was like, those don't really connect, right? Humans, machines, they're all different. And I sort of lucked into industrial and systems program where the focus was on understanding how systems work, because technology and people are part of the systems that we need to build for. And that's how I learned about human factors. And as I learned more about human factors, I found that there were multiple roles that human factors engineers can take in the field. They can do systems design and evaluation. So the way we evaluated smartwatches and smartphones, that's something that human factors engineers do. All of the sort of in-dash infotainment systems that are in cars these days, those are things that can be evaluated using human factors analysis. Human factors engineers also do human performance research. So we understand the capabilities and limitations of humans in order to better build guidelines for technologies that work within those capabilities and limitations. We can study driver behavior to, provide policy recommendations or recommendations to designers and companies. And we also do industrial and occupational safety. So we try to understand how to build safer environments for our workers to work under. And these roles can be found in many different companies. There's consumer technology companies like Apple, Google, and other usual suspects. There's car makers like Ford and Toyota and GM. And there's also research groups and consultancies that do a lot of this work. So things like Battelle, which does a lot of government research, private consultancies, they all require this skill set because the future technologies all require understanding of both the users and the technologies that the users are interacting with. Okay, I'll be happy to answer any questions.
One question.
Sorry, I actually participated in a transportation study a couple of weeks ago, and I found that that the camera that they had on my eyes to track my eye movement actually limited all of my visibility and comfort while driving. So I was just wondering, like, how do you make sure that the situations that these people are in are not only comfortable but as real to life as you can?
That's a great question. Partly it can depend on the eye tracker that's used. I'm not sure which eye tracker system that you are interacting with, but there are head-mounted eye trackers like what you described, and even within those, there are ones that are more comfortable and less comfortable. There are dashboard-mounted eye trackers, and there's a sort of other methods we can use. So experiments are one of the methods we use to understand behavior, but they have limitations because they do take you out of the natural driving a car. So we often support that with more naturalistic studies. So we might instrument cars with cameras, and then we might go and observe people within their own cars and see what they're doing. So it requires a bit of combination between all of these different sources, each with their own limitations, to really understand driver behavior.
So I'm going to have to be kind of mean on the timekeeping since we have so much. Thank you so much. That was great. And the clicker is up at the front.
Okay, cool.
Hi, I'm Justin.
Postdoc in occupational therapy, as previously mentioned, but I'm not an OT. My background's in psychology, exercise physiology, and then sports psychology. All over the board, very different than pretty much everyone else in the room. So that could be a benefit or that could be a curse. So I'll tell you a little bit about one of the projects we have funded through STRIDE, Older Drivers' Perceptions of Autonomous Vehicles. I'm here representing my boss, Charlene Clausen, and then the rest of the team. So autonomous vehicles, you'll probably hear enough about that throughout the day. We look at how people interact with these and their perceptions to autonomous or connected vehicles. We're a little bit more integrated with quality of life, and that's why I think we work directly with engineers to get that balance. We also look at safety from a different aspect. Mobility, independence, all of that's important to us because I am representing IMAP, which would be the Institute for Mobility, Activity, and Participation. So we look less at the efficiency of a machine and more about the practicality and feasibility of it. And then we also want physical activity, and we want people to stay active and healthy, which may not be occurring if everyone's using an e-scooter to get around, but that's probably another discussion to be had. So again, we use a multidisciplinary approach. Transportation engineering and OT overlap in this beautiful Venn diagram that I'm sure you guys use a lot while you're teaching. This one's not very pretty, but it gets the point across. Transportation engineering looks a little bit more at efficiency and safety, and we look a little bit more at teaching and training individuals, whether it's older adults, teens with ADHD, individuals on the spectrum, people with mobility dysfunction as far as like spinal cord injuries and whatnot. And then again, we just try to enhance quality of life. And then we have all of these jargon terms that you see on the outside, IVAS, ADAS, basically information that's provided to a driver, or assistance and automation that's provided to a driver. And then you have all these terms which get confusing because different makes and different manufacturers use different terms to explain their technology. So that's kind of a role that OT can have as far as training individuals to let them know what their vehicle can do, what it can't do, and when not to let the vehicle take complete control. Community impact. So we're still waiting on a waiver from NHTSA, which is the National Highway of Traffic Safety. You could just kind of think of it as part of the U.S. government. So we are not allowed to put the autonomous vehicle on the road right now on public roads. So that's kind of delayed some of our projects. So we've been using the old RTS depot, which is right by Depot Park, which is a blast to get older adults out there. It's a very difficult place to maneuver. But we were just looking at older drivers, 65 years and older. And then we have another project with individuals with spinal cord injury and or disease. We're working with the city of Gainesville, and it's obviously funded through STRIDE. And we're just looking at their perceptions to the autonomous vehicles. So we expose them to an autonomous simulation, which would be on the driving simulator. And we also have them ride in an autonomous shuttle on the road, really in like a testing area. And we just compare pre to post and see if that exposure helps or hurts their perception. So really no intervention other than just exposing them. There's various phases of testing, so we're trying to get that AV out on the road so that everyone can utilize it and see what it's all about. But again, NHTSA is kind of holding us up. I have a few pictures of the shuttle. The top speed is 28 miles per hour. That's not very fast, but it does the job. It also helps a little bit with safety and trust of the vehicle. So here's a picture of the AV shuttle. It kind of looks like something from like Doctor Who or I don't know, maybe a toaster. I think a toaster would be more fitting. Maybe hamsters will like jump out of it, like one of the newer Kias, or whatever brand that is. So the door is basically open, and I think I have pictures of the inside. To the left and to the right, and then in the middle, there's basically two like chairs that you can kind of stand, sit on, more of like a bar stool. So if those of you want to drink after work, you just jump on the shuttle, have a drink or a few 15, and then keep riding home. Yeah, pretty straightforward. I'll show you a few more pictures, I believe. And then here's the image of the driving simulator. In OT, we work with different populations, individuals with Parkinson's, those that are going to be distracted, which Wayne pretty much covered, individuals with ADHD on the spectrum, older adults, multiple sclerosis, veterans. We have a few different studies going on with vets right now, and seeing if we can kind of retrain them to drive on the road safely and
and then how marijuana affects driving too. So we're kind of all over the board. Whatever gets funded, we do, and it's fun too because then we're not just stuck working with one population. Not that working with one population is bad, but it's cool seeing the entire lifespan and spectrum. So career opportunities, I think a lot of this will be covered today. Lately, we've been interacting with AV operators and engineers. Various backgrounds. They're not the typical engineer as far as like having a PhD or even an undergrad degree in engineering. That's just their title. They're the ones operating the autonomous vehicles. We have Smart Driver, which is a service to help, and the CDRS stands for Certified Driving Rehab Specialist. So we help assess driving needs, and we see if someone's safe to be on the road. That's pretty much anyone with a clinical background that then becomes certified as a driving rehab specialist. Researchers, and then there's also that in between of what do researchers find and how is that relevant to the regular population. I have no p-values or effect size on here, so trying not to bore you, but there needs to be translators as far as like what did we find, and maybe finding a better means to provide that information than maybe like an article that might be misleading in some of those outlets. Clinicians, manufacturers, startups, industry, and then again, that multidisciplinary approach for road safety and simulation. I just kind of wanted to mention another media forum, which would be the Road Safety and Simulation Conference, which is just a culmination of human factors, engineering, psychology, people in industry at FDOT, you name it, they'll be there. So that's a cool website to check out for more information, just as far as jobs and how we all work together. And I can leave that up for a second.
Great.
Will this be shared?
Yes, so I will, as long as the speakers are okay with it, I will share all of the presentations, and we are recording, so hopefully this will all be recorded, so I could even share a recording if you'd like.
All right.
So if we could, one question?
Quick to the point.
One burning question. Okay, great.
Thank
Thank you so much, Justin. Okay, and now, okay. Moving right along.
Morning, everyone. My name is Carlos Soler. I'm a PhD student in the Structures Department. I'm here representing my PI, Dr. Bridge. I'm going to talk a little bit about the projects that she does that are related in some way to infrastructure that transportation depends on, so bridges. The key thing that we do in her lab is instrumentation, and we either design sensor systems, we either design the actual sensors, or we organize other people's sensor systems. So we're going to talk about 3 projects. The first one is related to UAV, unmanned aerial vehicles, bridge inspections, organizing sort of the logistical part of all the instrumentation, like weather stations, GPS that the Sunshine Skyway Bridge has, and my project, which is monitoring, structural health monitoring of coastal bridges. So the UAV project. So UAVs in this project are trying to be designed to be a replacement to routine bridge inspections and damage bridge inspections. So bridge inspections are typically scheduled every 2 years for the most part, and special bridge inspections for when an extreme event like a hurricane or an earthquake happens, that you have to like sort of schedule special bridge inspections to detect those damages. So for regular bridge inspections, you a lot of times need to block traffic, you need people there, and you sometimes need boats if your bridge, which a lot of the time passes over a river, and this causes a lot of logistical challenges. With unmanned aerial vehicles, you don't need any of that. You just need a couple people and one pickup truck or a boat if you need to go under the bridge. So here's a picture of the UAV that was designed for this project. You can see it has GPS, a high-resolution camera, a laser finder, an optical flow sensor. So this is what's really innovative about this specific UAV project. It can when you're flying a UAV under a bridge, typically you need to depend a lot on the pilot, and with any kind of wind, that becomes a hazard, and it can't guide itself with GPS when it's under the bridge. But with this optical flow sensor, it can detect the distance that it is from the bridge, and it can sort of guide itself. So this provides great opportunities for the camera, because that means that we can take a lot of pictures, and actually you'll see later on, we can actually reconstruct a 3D image of the bridge and show damages in great detail. That without this, you would have to get a person there with a camera and take multiple pictures of. So here's an example of what I mean when you complete a pickup truck. You launch it from there, and you pilot it from there as well. Here's an example of the team we need: an inspector, a visual observer, and a pilot. So this is what has been done with this project. Bridges with differing challenges have been inspected. Ones where a boat was required. Ones where you needed to go under a bridge that had a road underneath, and you know, some mistakes happen. You know, we may or may not have needed to retrieve the UAV from water, but that's part of research. You know, you make mistakes and you write it down in a notebook and try again. So this is what I meant with the optical flow mode. It can you set a distance and it will stay at that distance from the bridge, and these are the kinds of images that you can take with a UAV that can guide itself. And this is what you can reconstruct with thousands of pictures. This is something that you can have in a computer and rotate and look at from all kinds of different angles. This is a real picture, and this is digital. So these are sort of the pros and cons of what this UAV project provides, as opposed to a regular bridge inspection. And yeah, there are a lot of UAV projects for bridge inspections being done, but what makes this one different is that ability to for the UAV to control itself while it's flying under. It makes it safer, and it makes for better opportunities for inspecting the bridges from different angles. So the Sunshine Skyway Bridge project was really interesting and different from what we usually do. This one, here's a picture of the bridge. This one required us to basically get a bunch of different FDOT agencies together in telling us what they have on the bridge, and giving us sort of permission to then say, okay, well, there's another agency that could use that, or if you give us access to all of that data, we can reconstruct a better image of what that bridge is undergoing at any given moment. So here's a little bit of history of the bridge. It was built in 1987. It has an average daily traffic of 50,000. It's over 4 miles long, and if anyone's been down to Tampa, it's very crucial for transportation. So that's why it has a lot of stuff on the bridge. Everybody wants to know what's going on with this bridge, and they want to know if something goes wrong, what happens. So phase one, as I said, just get a list of everything that is on there from everybody, and see if you can get access to that, and be able to just provide communication with everybody and everybody's devices. So here's a list of all the agencies that had sort of real estate on the bridge. With, you can see just, you know, how many weather stations can you see? There's this agency has 2, this one has another one, and this one has another one. You don't need 4 weather stations on one bridge. So this is the kind of inefficiency that comes up when you have no communication between different agencies. But the good thing is that with all of this data in one place, say like a website that everybody in every agency can access, you can build stuff like an FEA model, a finite element design of a bridge, can then analyze on a computer. So, for example, this bridge has accelerometers and it also has GPS. For very slow movement, GPS is good, but not so much accelerometers. For very fast movement, accelerometers are better than GPS. So this is the kind of thing that you can build a full picture of what's going on with the bridge. Okay, so now moving on to a project I can actually ramble on about. My project, the Coastal Bridge Monitoring Project. So this is one example where we actually design a sensor network for a specific task. So the aim of this sensor network is to be rapidly deployable, robust, and inexpensive, spatially dense, and can measure more than just one thing. Say, for example, we not only want to measure wave forces on a bridge, but we also want to measure the bridge response with accelerometers to these forces. So in the past, like in Hurricane Ivan, Hurricane Katrina, bridges in US 90 and other roads, they have been with a combination of hurricane surge and waves. The bridge decks have literally been taken up, they become buoyant and pushed away, and that is not good because first responders and evacuation depend on these bridges. In states like Florida, Mississippi, Texas, their largest population areas depend on these coastal bridges. So clearly there's attention that needs to be put on the design of these bridges for wind or for hurricane surge and waves. So this is an example of what we're proposing. These are pressure sensors, one pointing outward, one pointing downward, that we put on the bridge piles for now. So the bridge, the system design contains the sensors, the sensor hub that's above this, and the base station that communicates with back and forth with the sensor hub. So part of the challenges are power and communication. You know, you're in a isolated place which may not have power. Non-destructive bridge attachment, we want this to be applicable to more than just one bridge. So we need to come up with attachment methods that apply to many bridges. You'll see here metal strapping. There's other methods that we've been trying, and it has to survive exposure to the elements. We want this to be removable after a hurricane. So this is sort of a diagram of how everything works at the moment. You have the sensors, which are attached near the water line. You have the sensor hub, which is wired onto the sensors and communicates with the wire. And that sort of contains all the hardware and software that actually records the data. And you have the base station, which communicates with the sensor hub via Wi-Fi. And the base station is sort of located a little bit off of the bridge, but close enough to be able to communicate, but far enough away to be safe. And that communicates then with a University of Florida database via cellular signal. So this is an example of data that we can record with this system. This is the sensor that we have deep underwater that's sort of measuring the water level, and these are the sensors that we have at the surface. You'll see here we measured a nice little wave impact that I'm really proud of, and we also measure atmospheric pressure in order to get in order to get a gauge pressure. All of this is absolute pressure. And sort of as a sanity check, we also want to check our water levels with NOAA. So you can see the orange line is NOAA and the blue dots are us. So it works. For future deployments, we plan on deploying at the Skyway Bridge again, but also at Matanzas. Matanzas is in St. Augustine, and it's a much more isolated bridge. It's the highest structure anywhere around, so we have to rethink about the concept of the base station, because initially we wanted it to be far away but safe, but in this case the safest place is the bridge. So we have to redesign sort of the system for these challenges. We're applying solar panels because in the Skyway we have an outlet nearby, different things. We validate these results by wave tank testing. And here's a picture of Matanzas. You can see that there's nothing around. So the bridge is the safest place, ironically. UAV bridge inspections provide new opportunities and a safer method of bridge inspections. Sunshine Skyway Bridge highlights the challenges of a logistical sensor network design. And the Coastal Bridge Monitoring Project will provide a better understanding of wave loads on coastal bridges. Thank you.
One question?
My question, Sarah, is, okay, so it's communicating by cellular, right?
Yes, the base station communicates with the University of Florida via cellular signal.
So what happens if the cellular signal is no longer communicating? Is there any other kind of way that it can have the communication continue?
That's a good question. So when communication fails, which is very likely during a hurricane,
Right.
We save the data that we record locally on an SD card.
Mm-hmm.
And then, we can retrieve it afterwards.
Great. Everybody's doing a great job of staying on target with time. We're doing really well, so thank you. Okay, so we have 3 more speakers. Patrick Amami, is next. And you have your clicker.
Hi, everyone. I'm Patrick Amami. I'm a PhD student in the Computer Science Department. I'll be talking today about our lab, and the title of the talk is Video-Based Analytics for Intelligent Transportation Systems. So my lab, as I said, is in the Computer Science Department. The PIs are Dr. Sanjay Ranka and Dr. Anand Rajan. And broadly, we're focused on intelligent transportation systems. A definition I like to use for intelligent transportation systems is the use of cutting-edge synergistic technologies to develop and improve transportation systems of all kinds. As you saw, the last talk, this extends beyond just cars and pedestrians. But primarily, our lab is focused on urban mobility. That is, pedestrians and vehicles in urban settings that are now becoming more and more connected and autonomous. So the primary push of our lab is actually looking at sensors and the types of big data you get, but in the context of the infrastructure of transportation. So a lot of people that are working on big data analytics in this space are building it for applications within self-driving cars. However, our lab is focused on the infrastructure side and how we can take insights from the big data you're getting and combining that maybe with the data you're getting from the self-driving vehicles themselves. In this picture, this is a snapshot of a traffic camera here in Gainesville, where we've extracted the types of objects in the image. And so primarily our lab is focused on video, but now we're expanding into other sensors. The lab itself is relatively new, and so one thing we've started recently doing is looking at other sensors beyond video, such as at the bottom here. This is the bottom one is a LiDAR. That's a laser sensor. It's used to get 3D pictures of the surrounding environment. On the left, that's a radar, and on the top, that's it's called a DSRC. It's a radio. This is what's used to do the communication between vehicles and infrastructure, vehicles and other vehicles. And our goal in this lab is to get big data streams, do analytics on that, so extracting useful information for a variety of end users like local governments, industry partners, and making that information available to them so they can make decisions to increase the safety and efficiency of our transportation system. Okay, so the rest of the talk, I'll be kind of just going broadly over a variety of problems in this space that our lab is now becoming more and more focused on. We want to use to try to build new solutions to these problems, to provide the information to, like I said, local governments and other people who may be interested in ways of making our systems more efficient, but being able to do so in an automated fashion. So one thing we're focused on, of course, is safety, and we want to use video solutions to do that. So you can think about it like asking these types of questions. Are pedestrians crossing the road at a traffic intersection? If you have a camera, it's actually not so easy to answer this question. The camera only sees an image, and what we want to be able to do is actually determine if in any image, is there a person? Are they trying to cross the street? Is the light actually, red for that road so they can cross safely? And the image I showed earlier, what we may be wanting to do with that type of data is count how many vehicles are at the traffic intersection. That type of information is definitely useful for, say, urban planners who want to adjust the signal plan so that they know how much volume is a certain traffic intersection getting in real time. Right now, we don't have that many ways to get real-time updates to our signal plans. We don't really have this type of automated analysis set up yet at our intersections. Another safety type of application at traffic intersections that you can address with video is answering the question of, are vehicles driving the wrong way? That's definitely a safety concern, and being able to, in real time, alert the proper authorities or if somebody can do something is definitely very useful. So what we're trying to do in our lab is look at the software, the type of analytics that you would do given these data streams to answer these types of questions. So one problem that's kind of at the core of these types of systems that is given these types of data streams, say from a traffic camera at a traffic intersection, or in this case, installed on a vehicle or placed at a traffic intersection from this is a 3D picture of the scene with a LiDAR, is actually looking at not only where are the objects, but also over time, where have they been and where are they going. This could be used to do behavior recognition. So using the information about where are the pedestrians, where are the vehicles, where have they been and where are they going, can we identify then are they trying to cross the road? Are vehicles about to collide, or have they collided? And you could do even more sophisticated things like modeling merging zones, for example, and all from having the ability to extract these trajectories, that is, sequences of positions over time of where the pedestrians have been and where they're going. You can also imagine the type of analysis you can do with this information could be used for things like understanding, are patterns changing? So is there, say, a road blockage at a traffic intersection because you detected that all the vehicles have stopped turning a certain way, or they're all swerving around a certain obstruction? And we want to be able to do this automatically in real time using the types of sensors that I've mentioned before. Another interesting application of this type of technology could be collision prediction. So in this case, say you have a UAV, so like a drone, that's positioned on top of a traffic intersection. What we're interested in is studying the problem of, can we actually predict collisions as they're happening? Or if we're looking at a video that's been recorded in the past, can we automatically extract collision events and then use that to analyze the design of the intersection, for example, and maybe make decisions to improve future designs. Finally, I'll just mention another application is 3D mapping that we're interested in as well. This was also brought up in the previous talk. So primarily, 3D mapping is used for the actual autonomous vehicles. They need this to navigate in urban environments. But we're also interested in looking into doing 3D mapping of the urban roadways and traffic intersections, primarily, say, to share that information with self-driving vehicles, to make it available for better analytics from both ends. So from the end of the autonomous vehicle and from the perspective of the traffic intersection. Now, so I just went through like a bunch of different problems in this space. So once you've developed these types of skills, what can you do with that? Well, primarily, now that autonomous vehicles has become such a, it was becoming such a big thing in the industry, there are plenty of positions at places like Waymo and Tesla, Uber, and so on, for engineers with these skills. If you're interested in the research side of things, there's plenty of roles in both industry and academia, places like the Toyota Research Institute, where you can take your skills that you've developed in analyzing big data from sensors and develop new and improved systems. And of course, in industry, there's plenty of now companies that are building these types of systems to sell to various, like City of Gainesville, for example, and so some of those would be image sensing systems, MyoVision and GridSmart. And so, as I mentioned, City of Gainesville, they currently have, for example, GridSmart product where we have a variety of cameras all over Gainesville that we're able to gain access to these video streams. However, there's not yet a very nice way to extract that information and do from these video streams and do something with it that's useful for the city planners. So that's kind of where our lab hopefully will come in, where we can take the video streams you're getting from the GridSmart cameras and make solutions that they can use in real time to do a variety of different improvements to safety and efficiency. All right, so thank you very much.
Great. So any time squared. Do we have one question that we'd like to pose? I had a question. Patrick, could you describe what big data is for anybody who might not know much about what that is?
Sure. So yeah, the term big data has been thrown around a lot. I guess the way I would describe it is nowadays everything is becoming connected. So I talked a lot about traffic cameras, but we also have other devices like smartwatches, our cell phones, that produces a lot of data that we would like to do analytics on. And so you can imagine companies like Google that build these, and Apple that are building these technologies, they're receiving these data streams, and they're doing a lot with it in terms of analytics. But companies are not the only people that are receiving these data streams. There's local governments like City of Gainesville that are also receiving tons of data every day. When I mean tons, I mean if you have 300 different video cameras streaming video to the City of Gainesville, and every day. That's a lot of data, and so when we say big data, we're not only talking about the actual data stream. We also want to talk about the analytics as well. What can we do with that data to extract insights, things that we can then use to automatically improve the quality of life of a lot of people, in our case, improve safety and efficiency of transportation systems.
Great, thank you. Okay, Brendan next.
So I'm glad I got my friends up here. So I'm Brendan John, like I said before, PhD student here at CS people. So my advisor is Dr. Aika Jain over there, and we work a lot with Kiva. So that's kind of why I'm here. And we're funded by FDOT, and I think we're also under I-Street, I believe. Cool. So very fancy title, but a lot of words. So impact of visual attention, or visual and audio alerts on driving behavior, and exploring visual attention through eye tracking. So I'll try to explain that kind of piece. So first, let's just kind of start with the research problem. Safety is very important for transportation. So commonly, Florida comes up as the most dangerous state for pedestrians due to several big cities. So in 2008, 2017, we see over 5,000 people died for pedestrians. On a yearly basis, we're seeing over 100 people in Florida die that are bicyclists being hit by vehicles. So FDOT wants to solve this problem, or at least help. So highlighting vulnerable users looking at pedestrians, so people are just walking around, bicyclists, but also we started to focus on children in school zones. So I like going last, because a lot of people have already talked about this. Of course, we're building towards smart connected cities. Vehicles talk to other vehicles, vehicles talk to lights, lights talk to emergency responders who get to incidents when it happens. This is still a long-term goal. So locally, we're starting kind of first at a lower level. So our short-term goals are how can we improve safety in Gainesville school zones, and also for safety of pedestrians and bicyclists here in Gainesville. So our actual work is done, we didn't develop the app ourselves, but we work closely with a company called Applied Information, and they developed an app called Travel Safely. So similar to Enlighten, which Stephen mentioned before, you can go download it today. So it's called Travel Safely, one word. It may say glance Travel Safely if you go download it, but you can go to Android or iOS today. Very simply, they just use GPS to track people driving around, bicyclists, and pedestrians. They've also, so I mentioned school zones, worked to connect 6 smart school zone beacons within the city of Gainesville. So Temple incorporated people who did the hardware side of that. And in our own research, we conducted a user study to evaluate the impact of this application. So technically it's in beta testing right now. You can go download it, but they're not really advertising it much. So we wanted to kind of take an initiative to see what is this, how is this working with actual drivers. So just to give you a video explanation.
Took a little while to download yesterday, so it's working.
Okay, I thought you were going to download the full EVPs.
Yeah, it didn't, I don't know.
Okay,
there we go.
Here we are. I think that's it. Try it again. We'll go.
And then just hit the play.
You click on that.
Oh, yeah, sorry.
Okay, cool. So this is, okay, first. So all this requires you to have a mobile phone in your vehicle. Generally it'd be synced to the Bluetooth speaker. Okay. Yeah. So this is the flashing active school zone beacon. You'll notice something changed. They press over the text.
Heating in school zone.
And then it goes when they slow down. So very simply, it's looking for GPS locations whenever you're entering a school zone. Using GPS, it knows how fast you're driving, and it can tell you if you need to slow down if you're not in the school zone. Similarly, this one loads,
Do I need to click on that one too?
this alerts for bicyclists as well.
Cyclist ahead.
That's mostly what I want to show you out of this video. So there's alerts on both sides of the coin. So the driver themselves get alert that there's a cyclist ahead, but also the cyclist gets an alert that a driver is coming and potentially could be hurting them. And another thing, I guess, Wayne started talking about a bit too, is eye tracking. So while we're evaluating this app, we also want to study human perception, how humans behave in general. So let me start the video. So this is an example of our eye tracking setup in a real car. So we place it on the user, and now we have this essentially video, because they're wearing this pair of glasses, that says what they're looking at, and a little orange dot that jumps around that kind of measures what they're actually looking at while they drive around. So this is pretty common for psychology studies, as we saw before. A lot of people want to understand how humans behave. So it's a little bit dark, so you won't be able to see it. Essentially, we're just pointing cameras at your eyes, figuring out where your pupils are, and have a camera front facing forward. So this is just one pair of glasses. So we'll talk a little bit about our study. So we have 50 licensed drivers that we recruited and paid for their time, of course. Everyone had to be a licensed driver. They drove a designated route 2 different times. They passed through 4 different school zones. And what happened is they had the app in the vehicle. We also planted somebody around their route that was bicyclist. So they're on the side of the road pretending to bike around. And they would have the app on, so they would trigger alerts. As we designed our study, we had 3 different conditions or groups, visual plus audio alerts. So you saw in the video, I can mount a phone right up there while you're driving, you can see it. So I can see navigation, other things like that, but also get my alerts. But we also looked at audio-only alerts. So as we talked about texting and driving and distractions, by giving you these visual alerts, this big red exclamation point that pops up, it's not going to distract you and take your eyes off the road, which is actually a negative effect. So we want to look at this audio-only, and plus we have a control group where nobody gets alerts. This is kind of the naturalistic driving, how do people behave. So this is the route itself, Northeast Gainesville, so airport's right up here. University of Florida East Campus is right there. So they would start their route, drive down Waldo, go through. So we cover a few schools, Rawlings, Howard Bishop, and Metcalf are the major ones that we're hitting with this school zone route that we're traveling. There's a few spots that we would place bicyclists. We usually would have 1 or 2 people out on the route when they drove. Generally, we'd use this most just because it's high speed, and it's very likely for you to get to 45, 50 miles per hour, where we would get nice alerts for bicyclists. So we just finished data collection a few weeks ago. Actually, Carlos is one of our participants, as we mentioned earlier. So we kind of just barely started to dig into the data itself, and that's kind of where we're coming out here. But one of the pretty obvious hypotheses is, do the alerts actually cause people to slow down? So we're using GPS to track their velocity as they drive. So you can see these little blue sample points here, other instantaneous velocities, and we can kind of mark up the speed limits too. So we have GPS, we know where they are. So this is a pretty nice case of they're stop at red light, sped up, approach school zone. You see them slow down, and they actually very quickly drop below the speed limit, and to actually a very, very low 10 miles per hour. Once we hit the end of the school zone, so the school zone is this little dip in speed limit here, they speed back up as they normally would. So this is just one participant very early in our testing, but we want to look at what's the percentage of time that people spend speeding in school zones, particularly when the app is off. We want to see for each group, are people responding differently? Another cool thing, we want to talk about eye tracking. So we put these eye trackers on to see what people are looking at. So by giving people these alerts and letting people know about school zones, we want to see do people actually react in the future. So if I'm giving you this app and you keep getting all these notifications, people start to look for school beacons. The reason we put these big flashing school beacons out there so you know you're in a school zone. Very easy to tune out while you're driving. Even with these flashing beacons, commonly people miss them.
That's the video. Oh, I think it's the next slide that has the video.
So there should be a video on that one too. So both these have videos, but okay.
Okay. Yeah, I didn't see a video on that one.
Okay, so we'll just go back to this one. So it would have been a video of someone driving up through, right next to Howard Bishop. Essentially, they look over to the beacon itself. They look back at their speedometer. So you're seeing this behavior where they keep checking the beacon, look at the speedometer, make sure they're below the listed 15 miles per hour. I think it's 15 or 20 minutes. And essentially, they start looking back to the road itself. The other part of our work is a little bit more exploratory. So while we could measure how often they look at beacons, how often they look at the text on the road, we're also interested in what do people look at while they're driving. So commonly, driving research, as like Wayne talked about, there's a lot of simulations. So that way I don't have to have you actually hit a pedestrian. Of course, simulation is very nice, but also naturalistic cases. So what do you do on a natural road? Humans behave very, very strangely, and that's why we look at humans and computers, because sometimes usually it's harder to figure out what the human itself. So we're trying to figure out in a real road, people have the side tracker on, what are they actually looking at? So when this video starts, it's a kind of a visualization, very different from what you saw before. Before you just saw an orange dot jumping around, very hard to follow. Instead, what if I only highlight the pixels you're currently looking at? So from the human side, we do have some knowledge about how the eye works and how it works in our brain and the visual system. And where you're looking, currently where your eyes point, is where your fovea is. And that's where you have the highest visual acuity. So while I process information in my periphery of something in the car, something that's coming out of look, where I'm actually extracting the most information is where my fovea is. So while you're driving, if you want to play the video, we can look at a few things. So this is just one example of someone driving. See, they watch the car in front of them. They check on the rear view. They jump to a few different signs as they drive around. The cars, they check the light as they approach it. This is a visualization we've been playing around with. We want to try to look at this data. We found, so basically for each person, we have about 30 minutes of driving data. Multiply that by 50, it's very, very hard to watch. So we've had a problem with that. We can always pay people, undergrads, high schoolers, anything else, but it takes a very, very long time to look at. So something we're working with is from the more computer science and machine learning side is can we take these videos that are essentially just a bunch of pixels saying what people are looking at and kind of analyze them to see, okay, how much are they looking at the road? How much are they looking at street signs? And at least in the school zone areas where we have video of how often are they actually looking at these. So right now we're kind of still trying to answer these research questions. We're at a point where we have all this data and now we have time to actually look at it. For careers in STEM, I think people have done a pretty good job covering this. There's software side of things, so application development. So of course somebody has to make this phone app. Someone has to make the integrated systems, smart beacons and stuff, transportation systems. So this is something more higher level. So if I'm giving you this alert when you're driving by a cyclist or a school zone, how early do I give you that alert? Is it super early and it becomes very annoying and then you just start to tune it out? Or do I wait too long and it's being too close and you start sliding? And so on, lots of theories there. From my side, I am computer science, but we work very closely with human-centered computing, so very similar to human factors. We want to understand how do humans and technology work together, not just making technology better. From the computational side, eye tracking is very useful for visual attention. So people train models to say for an image or a video, where are you going to look? This is very important for automated vehicles. If I'm trying to train something to act like a human and drive down the road, I want to know what they do. And vision itself is a very, very useful sensor for this. It drives most of our brain processes. Unless you're blind, you actually use visual input for a lot of things. So like I said, user experience design and human perception studies are a very interesting part of more human side of computer science. So it's also becoming very, very hot these days. So it's a very nice career path. Someone that's very, very socially inclined, but also very interested in applying technology. I think that's it. So I think we have time for your questions.
Question? No one? Great, thank you, Brendan. I don't know what that is. Go away.
You may want to enable.
Oh, is that the, how do I enable it? Now that I
Go
speak,
ahead and see
we'll
if you
just
have
see
any
how it
issues.
goes. And then,
All right, I know I'm the last person between you and the break. I totally recognize that. And Ondine, I know I have 4 minutes to present.
No, you have, I'm gonna actually go see if the shuttle's there, and I told him we might run a little late. You go ahead and take what you need, and I'll be right back.
All right, that's bad news for you all, I guess. So I'm with the Transportation Tech Transfer Center, the T2 Center, so people usually call. This was established back in 1984, 1983, even before I was born. We are conveniently located on the East Campus, so if you're heading to airport, on the left-hand side, you'll see US buildings, that's where we are. We don't have any parking issues. We have plenty of parking at the main campus. Newer buildings, space is not an issue there. All right, so what's our focus of tech transfer is really, our mission is to disseminate information related to transportation engineering. So we have three main units within our tech transfer centers, the auxiliary resource centers, and the third one is mostly developed based on research needs from most of our stakeholders. So auxiliary, like I said, mainly we do trainings. We do a variety of trainings, all the way from technicians to engineers and planners. We do some of the certification trainings, like the pilot expert and maintenance of traffic, that is needed by many of them in order for them to do the daily work. So if you see a flagger on the road, if you see work zone set up, they first need to be certified, and they have to come for us for this certification. And these have to be renewed every couple of years. So we do a lot of trainings every year. If you look at our website, you'll see hundreds of different titles of trainings. We don't offer that every day or very regularly, but we do have capability of offering over 100 different topics. Here, just to show you the numbers, if you look at the sessions, on an average, we have about 152 sessions every year. So if you're thinking about 250 working days, we spend about 150 days actually training. So that's a lot. Think about putting together a workshop. You have registration, coordinating the facilities, and then for certification, you have to grade the exams and have a database for certification, reporting to DOT. So that's a lot of trainings that we do on a yearly basis. The second unit is the resource centers. Now, many of you have presented that Florida is a focus state for pedestrian and intersection-related crashes. So the Department of Transportation has tasked us with providing more information on how to improve safety along those lines. Now, we can do all the improvements you want related to engineering, have AIs and stuff needed to understand where the problems are, but unless we as humans recognize what we need to do, it's difficult to improve safety. So with the resource centers, that's what we do. We set up events. We basically tell them how to bike safely or tell the drivers how to drive around the bicyclist safety. We also hand out some gears like helmets for bicyclists, pedestrians, just flyers, nothing else you can do for pedestrians. Basically let them know how to, how to basically be safe around vehicles. So we also give away some bicycles during events, as to promote more of those grants. Some of the safety campaigns we also, I think we need a clicker. So we also help the DOTs to develop some of the safety campaigns. Okay, I guess that's not going to work. We actually host the websites for them. We do some of the safety campaigns for the Department of Transportation. So the second and third area is basically our research, which are basically driven by the needs of the stakeholders. There are 4 different projects that I'm going to highlight. The first one is the Transportation Safety Center, which actually was originally started by Dr. Siva back in 2011, 2012. In simple terms, the federal government gives a pot of money to every state to improve the safety conditions that may be in terms of design, construction, or something along those lines. Now, every state has to decide how to allocate those fundings. Now, if it's in urbanized locations, they do have the capability and the resources and the staff to actually identify the problem areas and tell the state, hey, we have these problems and we need funding. But if you look at small rural agencies, they are understaffed. They also don't have the capabilities to actually apply for those fundings. That's where we come into the picture. We help them do the network analysis, data analysis, the crash analysis, identify what countermeasures can be implemented, and develop the package so they at least have a shot at that pot of money. So we have worked with 5 counties till date, and our goal is to work with 25 rural counties within the whole state. The second program is the Safe Routes to School. It's similar. Most of the schools, they have issues around them infrastructure-wise. For example, they might not have adequate sidewalks or school zones are not adequately set up. So again, they have funding available that they can apply to, but one of the requirements is that they have to fill out those applications and submit it to the Safe Routes to School program. And most of the schools, they may not have the time, resource, or the technical capabilities to fill out those applications, and that's where we come into the picture. We help those schools fill out the applications and apply for those fundings. The third project is the Shield and Transit project. Could you actually close the presentation video? Please?
Yes, sorry, I was just wondering if that was going to be. Okay,
Partition
didn't
able
able-
to print that.
Oh, thank you. Okay, let's try. I think it's working now.
All right, so how many of you all have experienced or witnessed a near-miss accident or a crash? Pretty much everybody at some point in their life, right? So the way safety funding works is that you need to identify the need that there is a problem. And right now, the only way to identify the problem is crash reports. So unless there is an actual crash, it's not reported to authorities. So the crash numbers don't really show where there are higher risks that people may face on a daily basis. So that's what we are trying to solve here, overcome some of the limitations of existing crash data and identifying newer ways to quantify where there are higher risks. So this is one of the projects they're working on. So Shield Plus is a system developed by Mobileye that can be retrofitted on buses or any vehicle
Sorry.
that will highlight some of the conflicts that the vehicle faces. So these are fitted in 10 buses, RTS buses here in Gainesville. If you can play this video.
I didn't realize it was going to start all of a sudden.
600,000 vulnerable road users worldwide are killed in road crashes every year, many of them due to crashes with large vehicles. Most crashes between large vehicles and road users occur due to significant...
Oh, no. Sorry. What did I do? I was trying to adjust the volume.
blind spots surrounding the vehicle. These blind spots pose the largest threat when turning. Mobileye Shield Plus is a revolutionary safety technology for large vehicles operating in urban environments, enabling early detection of cyclists and pedestrians, helping avoid injuries and fatalities. Using an array of strategically placed artificial vision smart cameras, Shield Plus acts as the operator's third eye, continuously monitoring the blind spots. Shield Plus provides real...
So basically, these are advanced driving assistance systems for transit buses that can help the drivers know where there's a potential pedestrian or bicyclist in their blind spots. Can you play this one? So this is actual footage from the bus. Most of us, when you're especially taking a left turn, we're just looking for a gap in the oncoming traffic. We don't really pay attention to the pedestrian until it's too late. At least here, it alerts the driver that there might be a potential pedestrian in the crosswalk. So that's, as far as the system goes, that will help the drivers, right, to alert where there's a pedestrian potential conflict. But what else can we do with it? With this project, we are trying to extend the application of that particular system. How are we going to do that? This is actually a screenshot of the telematics data from those units in Gainesville roadways. So we have the capability of highlighting where those hotspots are, where those events are occurring on a regular basis. What that gives us is an opportunity to look at some of the roadway characteristics. Is there a crosswalk there? Is there anything that we can do geometrically that can reduce these conflicts? Can we put up a pedestrian signal? Whatever, we have an opportunity to identify those problem areas before there's an actual crash. The others, so this is one of the examples. You can actually Google the street view and see where actually the pedestrian was at that particular point of time. So it gives us very detailed data on that particular interaction with the pedestrian. Not only that, on the other hand, it can also help us with driver training. So maybe there's nothing you can do geometrically, but what you can do is include this in the driver training process, make them more defensive, driving, be more careful while driving in certain areas or certain locations where there are tight spaces. So that's what we are trying to solve with that. The next project is the bike rack project. This was again brought to us by some of the stakeholders while we were going to different events. They started telling that, hey, when we actually wait for a bus for a long time, we figure out that there's no bike rack available for our bicycles, so we have to wait a lot more time for the next bus to come on that road. So we are trying to see if we can fix that problem. So the way we did it is we collaborated with the electrical engineering department. They had this pressure sensors that we're using for dental implant purposes. So we actually started with that and developed our own pressure sensors that we installed on the bike racks. So all that does is when you put a bicycle on the rack, due to the pressure, the sensor is activated, and we hooked up a GSM module, basically a cellular data frozen database, and connected to the app. Now the students actually know which bus, how many bike racks are available, if they're available or not. So that way they can plan their trip. So that's what we have. This is all the engineering, all the electrical components that went into developing those. And these are actually students that are installing on their bike rack. You can see it's just a strip with a tube, basically pressure sensors. As you just put the bicycle, it alerts that particular status. So those are the different projects that the T2 Center is working on. Any questions?